Welcome to lecture 16, another example of Laplace's equation. This is going to be our third example of how we solve Laplace's equation, and we're getting significantly more complicated with additional examples. Before we get into the example itself, I want to talk about another property that Laplace's equation has, and that's called uniqueness. Many solutions of differential equations can be shown to be unique. Laplace's equation is one of these. It has unique solutions, and this means that if you can find any solution, then it is the unique solution. And this motivates the time-old method of guess the answer and check to see if it is right. And if you don't like that, it actually is a method that is used to solve many different equations. Basically, if you can find the answer by guessing, if you can show that the answer is unique, then you have the complete answer. And even if you tried some other method, it would come back to giving you exactly the same answer that you had already guessed. So this actually is a valid way of solving equations, particularly those that have unique solutions. The more precise statement of this is that the solution to Laplace's equation is unique in a given volume if the potentials have been specified on all of the boundaries of that volume. And so if we have that situation, then we will have a unique solution to the equation. Now the book details a method you can use to prove the uniqueness of the solution. If you're interested, you can delve into that to get into more detail. I'm not going to go into those details here. The only thing I'll mention is that the basic notion is that you assume that you have two solutions, you take the difference of those two solutions, then the condition on the boundary is that the potentials are equal to 0 on all the boundaries, and if you can show that the only solution to Laplace's equation that's 0 on all the boundaries is 0 inside the volume, then you have proven the uniqueness of the solutions to the problem. Now, one thing that you might also be concerned about is the fact that Laplace's equation is a second-order differential equation, and usually that requires specifying two kinds of objects. When we have initial value problems, if it's a second-order differential equation, I need to tell you the position and the velocity, or in other words, the value of the function and the value of its first derivative. Laplace's equation is a second-order differential equation, but we're not solving it as an initial value problem. We're solving it as a boundary value problem. And by defining the function on the entire boundary, that's enough to guarantee that you get a unique solution. And so you don't have to also determine what the derivative is on the boundary. Just the value of the potentials on the boundary is sufficient to get uniqueness. And this also shows you that these proofs of uniqueness are not completely trivial. If you've sort of gone through thinking, well, I don't really need to know exactly how this works and so forth, I encourage you to take a look at how it's done in the book, because it will open up your eyes that some of these things are not completely obvious, and the way in which they're done is not actually all that complicated. You should be able to follow exactly how that works. Okay, now we're on to our example. We're going to take a infinite cylinder and place it in between two infinite planes. We're going to put a potential of 0 on the cylinder, and then we're going to try and solve Laplace's equation. And this looks like a pretty complicated problem, but we do know by symmetry, because there is no z-dependence to anything, that the potential can't have any z-dependence. We also know it makes sense to use cylindrical coordinates with a center in the center of the cylinder, and so we're going to have coordinates are going to be r, theta, and z. The inner circle is going to have a potential 0 on it. And if we're far enough from the cylinder, then it's got to revert back to the solution that we had when there was no cylinder. And we know that the potential in that case equaled minus E0 times x, because the field always pointed in the x direction. And if I'm far enough away from the cylinder, I don't really know that a cylinder is even there. And so our second boundary condition is not going to be that the potential is equal to a particular value. It's going to be in the limit as r gets very large. We want the potential to approach minus E0 r cosine theta, which is minus E0 x in cylindrical coordinates. this is the one subtle point about trying to solve this problem. Now let's get started with the Laplacian in cylindrical coordinates. You've seen this before, but I'm going to write it again. It's 1 over r d by dr of r d phi by dr plus 1 over r squared d squared phi d theta squared plus d squared phi dz squared, and the sum of all of those has got to equal 0. Now in our case, there's no z dependence, and so we can drop that last term, and our function is only going to depend on r and theta, so we really only have these two terms, the derivatives with respect to r and the derivatives with respect to theta, that we need to worry about. Now the boundary condition at r equals big R, that's on the circle, is just that phi is equal to 0. The boundary condition for large r is that we approach minus e0 r cosine theta, and that motivates us to make the guess that phi of r and theta can be written in the form f of r times cosine theta for all r. Then if I set f of big R equals 0, I satisfy the first boundary condition, and if I set f of r approaches minus e0 r for large r, I satisfy the second boundary condition. So the question is, can we force this form to be able to satisfy the second boundary condition? Because the first one we always can get it to satisfy. So let's take a look at the equation. Now, what we're going to do is we're going to take into account the fact that the second derivative with respect to theta of cosine theta is just equal to minus cosine theta. So I had a cosine theta that multiplied the first term that has the derivatives with respect to r, and I had a second derivative of cosine theta in the second term, but that second derivative just gives me minus cosine theta. So I have a sign change, which creates the minus sign in this formula. Then I had a cosine theta in both of those two terms, which I can factor out and get rid of because the whole thing is equal to 0, so I'm just going to divide by cosine theta on both sides, and I'm left with this equation that is a single equation with respect to r. Now it still looks kind of formidable. There's lots of derivatives and multiplying by r and other things like that. But let's take a look more closely at exactly what this equation says. So we're going to just make a guess that f of r is equal to some power, r to the lambda. If we do this, we find that inside the first parenthesis, after I take the derivative, I'll get r to the lambda, r times lambda, r to the lambda minus 1, which is just equal to lambda r to the lambda. And for the second term, I just get minus r to the lambda minus 2. Now I can take the derivative in the first case again. I have lambda times r to the lambda, so its derivative will give me lambda squared r to the lambda minus 1, and then dividing by r gives me r to the lambda minus 2. And you find if I collect up all those terms, I'm left with lambda squared minus 1 multiplied by r to the lambda minus 2, and that whole thing has to equal 0. Well, the way in which I can make that equal to 0 for all r is to simply choose lambda equals plus or minus 1. So we learned those are going to be the solutions. F of r is some constant times r plus another constant divided by r. And then phi of r and theta is equal to ar plus b over r, the whole thing times cosine theta. The boundary condition at r equals r, which says that the potential is equal to 0, requires us to have b equals minus a big R squared. And then for large r, the second term, the term with b, is going to drop out because at large r that's going to go to 0. And so we find a times r has got to equal minus e0 times r. Well, that just says a is equal to minus e0. So we get our final answer. Phi of r and theta is equal to minus e0r times 1 minus big R over little r quantity squared. You can say I made the second term a quantity squared, so it has an r squared in the denominator because I factored out an r from both terms in the equation. Okay, we've gotten our potential. Because it's a unique solution and we found the solution, that's it, we're done. However, we also would like to figure out what is the electric field, and so I'm going to just remind you what phi is. The electric field is minus the gradient of phi. And so I have to figure out, all right, how do I calculate the gradient in cylindrical coordinates? Well, I have the derivative with respect to r multiplied by the unit vector in the r direction plus 1 over r, the derivative with respect to theta, times the unit vector in the theta direction, plus the derivative with respect to z times the unit vector in the z direction. So when we plug that in, because there's no z dependence to phi, ez is equal to 0. When I look at the r dependence, there are two terms that have r dependence, and when I take their derivatives, I get ER is equal to E0 times 1 plus the quantity R over R, big R over little r, quantity squared, the whole thing multiplied by cosine theta. When I take the derivative with respect to theta, that's also not 0, so I get an E theta, which is minus E0 times 1 minus big R over little r, quantity squared, times the sine of theta. And now we'd like to check to see, is this electric field actually a constant in the limit where r gets big? Well, when r gets big, the second term in the parenthesis goes to 0, and so the electric field is going to approach E0 cosine theta times E hat r minus E0 sine theta times E hat theta. And if I look at the picture on the left-hand side, it shouldn't take you very much to convince yourselves, if you work out the algebra and use the fact that cosine squared theta plus sine squared theta is equal to 1, that you get that that thing is equal to E0 times the unit vector in the x direction. And that shows us that we're done. We're actually satisfying the correct boundary condition.